In our previous lecture, we have discussed about bias and variance. And today we will discuss about the regularization approach, specifically the ridge and lasso regression. So we have discussed the bias and variance, and then maybe we can discuss, start the discussion from this picture again. So usually we divide our data set into train and test for training the model, and then maybe for performance evaluation. The train set is used for building the model, and the test set usually we use for the purpose of performance evaluation of the model. So consider that we have a test set, and in the test set, these are our data points. Okay, these are our data points. So if we plot the scatter plot, then we will get this. Then we can train different kinds of models. Okay, one is just the linear model. So linear model, that means if we just fit a linear curve, linear line. Okay, just a straight line. So then the equation of the model usually we use like beta 0 plus beta 1x. Okay, that means it's kind of the y equal mx plus c. So mx plus c. So this is the straight line equation. Okay. So in this case, we can see that here the beta 0 is our c. If we consider this one is our beta 0, and m, this one is our beta 1. Beta 1. And the x, that is our the independent variable, and y is the dependent variable. Okay, that means x is our feature and y is the target variable. So on that case, if we fit the curve, then we will get this. And we can fit this curve using different methods, like maybe we can apply the least square method, we can apply the gradient descent method, what we have discussed in our another lecture. Now, what we can do, we can apply also some other models, like a polynomial model. Okay, here. And in this case, we can see that is beta 0, beta 1x plus beta 2x square. So if we want to fit using our polynomial, using this polynomial, then maybe we will get this kind of line, okay? This kind of curve. Or we can also use the higher degree polynomials, like this is the higher degree polynomials we have. Beta 0, beta 1x plus beta 2x square, beta 3x3, and beta 4x power 4. Then what we will get? We will get this kind of curve for the higher degree polynomials. Okay, then the problem we have, that is, we can see that if we apply just a linear model, and if our data set is actually not for the linear model, then we will get the higher error obtaining. Usually the higher error obtaining, we mentioned that the higher bias. Okay, higher bias. And then if we use the higher degree polynomials, we can see here that is the degree up to degree 4, and x cube here, x square, so up to degree 4. Then what it will do, it will just perfectly fit each and every point. Okay, so it will try to draw the squiggly line. So this squiggly line, actually it will draw if we apply the higher degree polynomials. in our training data set. So what's the problem of this? The problem is it will kind of memorize the data points, okay? Memorize the data points. That means though in training time we will get maybe we can say closely zero error, but in our testing time it will not perform well. So this kind of situation usually we call the overfitting, okay? Overfitting. So now it's better if we can maybe draw this kind of polynomials if our data actually perfectly fit for the polynomial. This is kind of polynomial, but it's a polynomial regression, okay? Lower degree polynomials. Then we will get this kind of fit. And we can see that maybe we will get that is lower error in training and also lower error in testing, okay? So that means it has the low bias and also the low variance. So we can see in this picture that if we have the degree of polynomials in x-axis and error in y-axis, and then if we just train one model, the train model, then maybe you can say the training curve or convergence curve. This is our convergence curve. The convergence curve is like this. So in this case, we can see that actually the convergence curve for training, this is for the training convergence curve. And if we have another that is part of the data set, usually we have that is for the testing. And for testing, we can see that the error is also high, but we can see there is the error for the testing curve is also that is the high. And we can see the difference, okay? The difference between the training errors and testing errors. And we can see those are just higher. So that's why usually this kind of model, you can say that they have the high bias and also high variance. High bias and high variance. So we can build the model like some model can be low bias with low variance also. That is maybe the on the case the training error, it will be like this. And the testing error on the same case, maybe we will get the testing error also like that. Okay? So in this case, we can see that there is a variance is low and also bias is also low. That means we can say low training errors and also variance between the testing and training errors are also very low. So usually these are the ideal models. Okay, we want these kind of models with low bias and low variance. But the problem, this kind of problem, we call already mentioned that for the overfitting problem, we will get the low variance, low bias. This kind of model has the low bias. Low bias, but they will produce the high variance. Okay? High variance. So if we build the model like this way, then we will get this. But how can actually from this model we can maybe build the perfect model? To get the perfect model, so this kind of models, what we have to do, we have to use some that is penalty. Okay, we have to use some penalty. A function with the penalty usually we call the regularization. So that means if we do the regularization, then we will get the perfect models like a polynomials with lower degree. How can we get that? So if we can see this equation, so this is the equation for our, that is our least square method, or we can say in our gradient descent we also use the same equation. Okay, this equation. So it is what? It is the original y minus of predicted y. This is the residual and then a square. So usually we call it that is sum of squared residuals. Okay, sum of squared residuals, and sometimes we also call it mean squared errors. And what we have to do, we need to do the minimization of this. Okay, this is the error, because this is the error. So we need to do the minimize. We need to minimize the errors. We want to minimize the errors. So usually in our objective function of our linear regression, we have this part, that is minimization of residuals, squared residuals. But now what I can do, we can do something like this, that is the beta 3 square and beta 4 square. So here is this, that means we can see here is the beta 3 and here is the beta 4. The beta 3 square and beta 4 square. And we want to minimize, we want to get, we want to minimize from this equation, minimum value from this equation. And now we can see that that is the based on the beta. So based on the beta, if we consider here the beta 3 and beta 4, the beta 3 and beta 4, then we can see here is the 5,000, here is also 5,000. That means even if we consider that is the beta equal just 1, beta equal 1, then it will, this value will be 5,000. And this value will also be maybe 5,000. So that means this value, this error plus 5,000 plus 5,000, that is 10,000. Even if we consider beta 3 and beta 4 equal 1, beta 4 equal 1. So that means it is not a minimization on that case. So when we can get the minimum value, if we assign here the beta 3 equals 0 and beta 4 equals 0, then this part, we will get just 0. And then just we will get the minimum error with this function, with this residual function. So it means that if we apply this kind of regularization, so for the regularization we have added this part, this is called the penalty. Okay, so we have added this penalty term, and if we add this kind of penalty, then beta 3 and beta 4, this will be just 0. It means that here is 0, 0 times x cube plus of 0 times x4. So that means it will actually ignore these two polynomials. Then we will get what? We will get just only beta 0, beta 1x, and beta 2x square. We will get just this part here. Beta 0, beta 1x, and beta 2x square. Okay, that's why we want to do the regularization to overcome this overfitting problem. That means to convert the high degree polynomials to just only a low degree polynomial.
Sir, what is y1 minus y1 hat?
We already know this because in our linear regression and gradient descent lecture, we have already know this. So we have discussed this one. That's why I didn't explain. That is yi. This one is the original y, and yi hat. This one is our predicted y. Original y minus predicted y. Yeah, I have that example also here. This data set in our linear regression. Am I audible?
Yes, sir.
Okay. So we have used this data set in our linear regression lecture. So where we can see that there is the based on the weight, we want to predict the height. So that means this is our target variable. We want to predict the height. So here we can see that there is the for the first point. This is the height, that is given height, and we can see that the sum of square residuals, it is just 1.4 minus of this is our equation, that is our line equation. So this one is called yi, and this is the yi hat. Okay, so in our linear regression and gradient descent lecture, we have already discussed about that. That means we can see that to find out the residual, there is the first y, the y1, 1.4, and minus of the equation. And then for the second point, there is yi is 1.9. Here is the 1.9, and then yi hat is this part. Okay, that means our equation. And the third one, we can say yi is 3.2. Here is the 3.2, and then this one is our yi hat. Okay, that is our equation, intercept plus slope times equation. So the same thing also we are using here. Here, okay. That means in this equation, the same equation, the sum of square residuals, you can say, also the mean squared errors, you can say. Okay. Is it clear now, yi and yi hat?
Yes, sir.
Okay.
আর সামনে যে একটা মিন বি ওইটার কাজটা
So mean B, that means we want to minimize this loss. Actually, SSR is loss function, okay? And sum of square residuals is an error, okay? So we want to minimize this error. And we want to minimize this error with respect to this B, okay, this beta. In any optimization problem, usually we have, that is the optimization variable. So here, the beta is our variable in this optimization problem. So usually in our least square method, in our linear regression method, we didn't use the beta, okay? So here we can see, that means, okay, these are the case. And we have like intercept and slope, okay, intercept and slope. And I already mentioned that there is the intercept and slope. We can consider this intercept as beta 0 and this slope as beta 1. Okay, so these are the beta. So we want to minimize this based on what? Based on these variables. In this example, actually we have two learning parameters. One is beta 0, another one is beta 1. So that's the beta. Clear?
Yes, sir.
Okay. For the regularization, we use the Ridge regression, we use the lasso regression, and we use the elastic net, okay? In linear in our regression methods. So at first, we want to discuss about the Ridge regression. So in Ridge regression, the equation will be, in this case, we can see that this is for our least square method, or we can say the gradient descent, whatever we can say. Usually we use this term, but this is additional. This is additional for the purpose of regularization. So in Ridge regression, the regularization term is, in this case, we can say beta square, yeah, summation of beta square. And that's what we have written here. This is the 5,000 times beta 3 square and beta 4 square. Actually, here we do the regularization using the Ridge regression. Why it is called Ridge, I will explain later. But here we can see this term in Ridge regression, this term is the added penalty. Okay, so that means original objective function we have, but now we have the added penalty. And this penalty, what it will do, it will actually reduce the weight of the higher degree polynomials, okay, higher degree polynomials, so that we can get the perfect maybe polynomials for our regression. So now one thing here, that is the lambda, okay, this lambda, and we assume that in this case we assume the lambda equal 5,000, lambda equal 5,000, okay, the lambda equal 5,000. Usually lambda is called the regularization parameter, and it controls the weights. That means we have two terminology. Here is the training and here is the generalization. So it controls the weight between these two, okay, weight between these two. So that means we can say this lambda, actually we can take maybe sometimes we can take large value, sometimes we can take the smaller value, but it has the impact on that. That is, if we take the large value, then what will happen? If we take the small value, then what will happen? But we have to use this objective function for our that is a Ridge regression. So Ridge regression is kind of regression, that is kind of linear regression, but we can say that we have the Ridge. That means we can say we have the penalty term for the regularization. Okay, so this is the penalty term, the added penalty term. And if we can there is see closely, what's this? This is beta j. What's the beta? Beta is our slope. Okay, beta is the slope. So we have the slope like y equal mx, and the m, those are we considered here the beta. So for this polynomial we can say beta 1 and beta 2. Okay, so that means this is m1 and this is m2. So like this. Okay, so beta is our weight, or we can say beta is our m. So in this equation, the y hat, we also have the beta, and that beta we have to consider the same beta here. Okay, y hat, we have the beta. Okay, we have the beta, because y hat is what? Y hat is our equation, the predicted equation, and the predicted equation usually we write like intercept plus slope times x, so slope times x. And then if we have more, if we want to use more degree polynomials like slope times x square. And in this case, this slope, usually we call it, this is 1 and this is the slope number 2. So it means this intercept, usually we call it beta 0. And then this slope, this is called beta 1. And the x is our the feature, and slope 2, it is beta 2. And x square, this is our square of that feature values. Okay, so that means in our y hat we have, this is y hat, this is our y hat, that is our predicted line, okay? Or predicted polynomial. So y hat, we have the beta, and here is also beta. So we can see that actually this beta square here, this is beta 1, because we can see that it will start from the 1. It will consider beta 1 and also the beta 2, beta 1 and also the beta 2. And if we use the higher degree polynomial, then it will have beta 1, beta 2, beta 3, beta 4. Okay, so all those things. Now we want to see the impact of our lambda. Okay, this lambda. So if we consider lambda just very big lambda, then what it will do? If we consider that is very big lambda, then am I audible?
Yes, sir.
Yes, sir.
Okay, thank you. Okay, so what's the impact of different kind of lambda? We can say if you just put lambda equal very big, then if we put here the very big lambda, like maybe 10,000 or 1,000 something, then uh, then to minimize this total function, actually what it will do, it will just assign the beta equal 0. Okay, every beta will be 0 on that case, because it is trying to reduce this. Even if you consider beta equal 1, then this part actually contribute more. Okay, so that's why it will assign 0 to everyone. And so what if we just if we apply the beta equal, the lambda equal very small, so if lambda equal very small, if we can consider lambda equal very small, uh, so for the lambda equal very small, that means we can say like maybe if we consider lambda equal 0, so on that case what will happen? uh, so if we consider lambda equal 0, then it will only count this part, okay, or only consider this part. Uh, so that means if we lambda equals 0, then it will only consider this part. That means it will do the same thing as our that is the normal linear regression. Okay, or maybe the very small something, there is a small amount of uh, value, like maybe 0.01 or something. Okay, so on that case, if we consider these values, then this beta, this part will be there is less significance on that case also, less significance. Okay. That's why we have to select the lambda appropriately, like we can say not the big value and not the small value, okay? Not the bigger one and not the smaller one. So for very small, so it will just fit like this way. Okay, the overfitting will again occur. Now the least square method, that means the normal, our linear regression, usually we can apply the least square method, or we can apply the gradient descent. So originally what it will do, if we consider just only we have just there is uh, the beta 1 and beta 2, this is beta 2, not the beta 1. Okay, beta 1 and beta 2. So that means what we have already seen, there is yi minus of yi hat. Okay, yi hat, yi hat, and then a square. Okay, then a square. So if we use the polynomials, like you can say the polynomials like we have just only this y hat is the just the polynomial like beta 1, and then maybe you can say x1, and then beta 2, x2, this polynomial. And yes, beta 0 is also there, but consider that beta 0 is just 0. Okay, beta 0 is 0. Then this will be the polynomial. So on that case, the square here is the square. The equation we will get like this. Okay, so that is yi and xi and beta 1 and x2 like beta 2 square. Okay, so in this case we have just two here variables, and we need to find out the optimal values of those. Okay, that is kind of, we have just two slopes where we assume that intercept each other. So that is the equation, the least square method, the optimization objective function, it will be this. That is the minimization of beta 2 and beta 3. Okay, beta 2 and beta 3. But using the regularization method, actually what we are doing, here. So here is also the same thing. That means this part is same. Okay, like the least square method, or you can say ordinary least square method. So here this part will be the same. Okay, this part will be the same, and we have added something like the penalty. And what actually the penalty will do? So it will do something like this. Okay, something like this. That is, maybe we can see that there is, if we use this ridge regression, on that case, the square terms, that means we can say beta 1 square and beta plus or beta 2 square, because summation is there. Okay, you can see the summation is there. The summation is there. Summation. So that means these values less than something. Actually, instead of just 30, we can assume anything like maybe any t, any threshold. So this is actually happens in our regularization method. That is, originally we are doing the same thing like this square, but we impose some form of constant. And if you can see this example, so the MSE, or we can say SSR, whatever you can call here, SSR, sum of square residuals, and we have the beta 1 and beta 2. And here is the beta 1 square and beta 2 square. So that means we can see that we have to set the threshold here, like beta 1 beta 2 square less than 30, less than or equal 30. If we set a threshold like this, then what will happen? We can see that if we consider beta 1 like 4 and beta 2 5, on that case we will get the beta 1 square plus beta 2 square, this is 41, and MSE, that is mean square error, it is just 20. And if we consider beta 1, beta 2, 3 and 5, and on that case we will get beta 1 square plus beta 2 square 34, and the MSC we will get like 23. And for this one we will get MSC, that is squared error, it is 25. But actually, though we can see those errors are lower than these errors. But the condition here, this condition, actually we will take only the beta 1, beta 2 values where beta 1 square plus beta 2 square less than 30, but these are greater than 30. These are the greater than 30. So that means we will not consider this one, that one, and that one also for finding out the beta 1, beta 2. And though they will provide us the lower error, why we are not, we don't want to consider this? Because though they provide us the lower error, but actually in training time they will overfit. So lower error means we can see that in this picture it is just fit perfectly, okay, that is for each and every data point. So that means here error is low, or we can say closely zero, but it will create our overfitting problem. So that's why we don't want this kind of fitting, okay, and we want just maybe you can say this kind of fitting, okay, this kind of fitting. So that's why we need to allow errors, but how much error we will allow, and that's what the constant is. We have added the constant, this constant, okay, this constant. That means we can say this sum of the errors here, it will be like less than 30, and on that case, so if we condition on this, then we will get this kind of errors. But this error may provide us the overfitting case, and we don't want this, and that's why we have just apply this constant. Now we can see that rest of the three values of the pair values of beta 1 and beta 2, and they will provide the less than 30, uh, that is beta 1 square plus beta 2 square, and they will also provide this kind of errors, this kind of errors, but those errors are greater than these errors, okay. But we have to find out the minimum error among these three, okay, among these three, which one is minimum. So we can see that 25 is minimum. So 25 is minimum, and 25 actually we got from the beta 1 equal 2 and beta 2 equal 4. So finally, from this equation, we will return beta 1 equal 2 and beta 2 equal 3. And here is this, that is the error. On that case, we will get the error like 25. This will be the minimum error. Okay. The actual problem is this, but we do some optimization theoretic approach. So these are, I have already discussed these things. So we do some actually our optimization theoretic approach. Optimization theoretic approach. So in this case, this problem, this is our we call this one as our, that is primal problem. Okay, primal problem. And then if we apply this one here, the Lagrangian method, then we will get the similar problem like this. Okay. So actually, this one is our original regularization that is objective function with the constant, but after applying our that is to make it dual and also applying the Lagrangian multiplier, we will get the same problem. And we have already seen this one, this equation. Okay, so that means here is the lambda, and then this lambda is regularization parameter. Actually this one is we call Lagrangian constant. Okay? Lagrangian constant. So here's the lambda is a Lagrangian constant, and then beta square, we already from here, this one is the summation of the beta. So our actual problem is this, and we formulate this problem using this way. Okay, that's why we got the lambda, and this lambda is this lambda. It is the Lagrangian constant, but usually we call it regularization parameter. Okay, and now how can we solve this problem? How can we solve this problem? So that means we have this optimization problem. Then how can we solve it? So for solution, we need to find out the closed form solution. So closed form solution, we can see that this is the closed form solution. Closed form solution, this is also an optimization theoretic approach. I think maybe in future, maybe in your master's study or maybe PhD study, you will learn the optimization theory, convex optimization, so those things, and the details. That means how can we convert this kind of the equation to a closed form solution. You will learn those things there. But for at this moment, I think this is very easy closed form solution to this equation is easy to find out the closed form solution. And here we can see that for finding out the closed form solution, what we need to do, usually we call the Q of beta. Okay, so here is the beta, then this is a closed form solution or function, where there is Q, and we can see that here is yi and xi and beta. Okay, so yi, xi, beta, and a square term is there. So what we will do, we will think about like yi, this one is one matrix, and x is one matrix, and this beta is also another matrix. So a square, that means if we want to find out the square of like resultant matrix here, one matrix and another matrix is there, then usually what we need to do, we need to transpose one matrix, then another one. So the same thing for finding out the closed form, we will get that y minus of xb. So here is that y minus of xb and y minus of xb again. That is the square, but these are the matrix. So we will find out like the transpose of it. Y minus xb transpose. Here is y minus of xb transpose. So a square, where there is a square, usually in closed form solution, we do like this way. Okay. So y minus of xb transpose and y minus of xb. Okay. And here is the lambda, and the we can see this is our beta square. So that means beta transpose beta. So here is the beta transpose beta, and lambda is there. And while the summation, actually, we can see that if we just calculate the matrix multiplication, summation is already there. Okay, so this one, this row, first row, we have to multiply with the first column, and then each and every term, this one, we have to multiply with this, and then this one, then summation of the second term, we have to multiply with the second term here. Okay, and summation. So that means summation are there. So that's why no need of summation, extra summation in this case. But this is called the closed form. Now, what we have to do, just we can see that here is y and where is y. So y transpose y. That means kind of multiplication. So y transpose, this is y, this is y, here is also y. We will get y transpose y. So y transpose y. And then we will get here y and then xb. So we can see here, here is y and here is xb. So here is the x and y is there. So beta transpose x transpose y. And from here, because this is y is transpose, okay, so that means the transpose is there. So that means here is y xb, so y x and b. Similarly, from here, this term, and if we just multiply this term and this term, so we will get y and xb, that means x transpose, so x transpose and beta transpose. Okay, so we will get like from here one and another one from here one, so we will get two. Okay, so that's why it is like 2 beta transpose x transpose of y. And then another term we will get, this is x transpose and beta transpose, and here is also x and beta. Okay, So that means it is like X transpose and beta transpose, and here is the X and B. So X and B. We can combine this X transpose and X transpose here. Okay. Uh, so here is this. That is the X transpose and X transpose, and then beta transpose is there, and also B is outside of that. Okay. And we have like lambda beta t. We can take the common between these two, because here is the beta transpose B and here is the lambda. Okay. But in this case, what we have to do, the lambda, this lambda, we will not use that lambda, just one with the lambda here. So to form the closed form, we have to add something. This is called the identity matrix. Okay, identity matrix. So we have to, instead of just using this lambda, we have to add this identity matrix. That is lambda times identity matrix. So this identity matrix will be the size of P. That means we can say it will be a square matrix, and the size will be the P. P, that means the number of features we have in that. Okay, so this will be our closed form solution from this Lagrangian equation. And then what we have to do, the next thing is we have to take the derivative of this closed form, because we want to find out what we want to find out the solution. Okay, solution. So what we have to do, we have to just take the derivative and set the equation equal 0. Okay, so take the derivative of this equation with respect to beta. So that means we can see the partial derivative of q of b, q of beta with respect to beta. So if we just do the derivative of this equation, then we will get what? So we are just taking the derivative with respect to beta. So y transpose y, this will be just constant. Okay? So it will be 0. So that means this term, this part we will get 0. This part will be 0. And we can see here in this case we have what? We have like beta transpose X transpose Y. Beta is there. So that means beta is just one beta. So this beta will be just 1. This beta will be 1. So what we will get? From here we will get 2 X transpose Y. So here is the 2 X transpose Y. The negative sign is there. Okay? Negative sign. We must put the negative sign is there. And then in this case, we can see here that is beta transpose, and here is beta. That means we can say it's kind of the beta square. Okay, kind of the beta square. So if we take the derivative of this beta square, then it will be 2b or 2 beta. Okay, 2 beta. So here you can see here, this is 2, and these are just constant. So it will not change the values, and beta is beta. So 2 beta. And now to solve this equation, we have to just set it equal 0. Okay, so set it equal 0. So now if we set here it equal 0, then we will get this equation. From this equation we will get, like, we want to find out the value of beta. Okay, the value of beta. So in this case we will get like this part will be, from this part it will like uh, 2, and then X transpose X plus of lambda IP. Okay, so here we can see lambda IP, and here's the beta. And this term is negative what? Negative X transpose Y. So that means we can see equal. Here is negative, so we can take it in right side. So it will be 2 x transpose y, x transpose y. So then what will be the beta? Then beta will be 2x transpose y divided by this term, okay. So then we will get like x transpose, so that means we will get this one, x transpose y divided by x transpose x plus of lambda, the lambda I, okay, lambda I. But actually x transpose x, we will get this term in denominator, that means here is denominator, and we can write this one as the inverse, okay. So x transpose x plus lambda ip, here is the inverse, and then the x transpose x, okay. So that means this beta we can now find out this beta for the Ridge regression using this equation, One thing we need to that is remember also, that means for our just linear regression using the least square method, uh, so we can find out the same thing like the what will be the value of beta using this equation. We can see x transpose x, but on that case no penalty is there, so that means no lambda will be there. Then x transpose y. So this will be the equation. We will find out the beta values, or we can say slope values for our least square method using or solving this equation. Okay, now we got that is the final solution here, final equation to solve our that is the values of different beta. So now the Ridge regression, we can say we can easily solve using this equation. But what's the difference between Ridge and Lasso? The Lasso regression is this, there is the same thing. It is also apply the regularization, that means penalty, but it uses different equations for the penalty. The equation is a little bit different. We can see that the lasso means least absolute shrinkage and selection operator. We can see here that is in case of the lasso, the penalty term is not a squared value. It is just the absolute of beta. Okay, so this is just the change, only a little change about that. So this is called the lasso, but it has the big impact. Okay, so instead of a square, we will use just only the just absolute value. So that is our lasso regression. Okay, the same thing, same all the things are, it will be the same, but the equation is there. Okay, this is the equation for the lasso. So in case of our, that is our lasso regression, if we can see that there is one data set like predicting the credit card balance, okay, based on what? Based on income, credit limit, credit rating, and whether the individual is a student or not. So these are the variables. So considering, we can say 4 parameters, we want to predict the credit card balance. So this is the standardized coefficients and the lambda values, okay, the different values of the lambda. And we can see that actually if we set the lambda value here, this is the lambda, kind of maybe 3000 or something. If we use the 3000, then the lasso regression, it will remove all the 3 parameters, like it will remove, this is the income, that means it will remove this, because we can say it is already 0 here, okay, it is 0, and this is 0, this is 0, so it is 0. And then the limit, okay? So the limit we can see here, and rating is this, so rating is this one, is a rating, and then the limit is this one, and then its student is that one. So we can see this one, that one, and that one. These three parameters sets to 0. Okay? Here is the 0 already, 0. That means the lasso regression, it will not use or it will remove the parameters, or we can say select the parameters or remove the parameters from the data set. And in this case, if we set the threshold equal 3000, then it will use only the one parameter. This is the parameter. This is the parameter value. Okay? This is the parameter value to predict the credit card balance. So that means that lasso regression, in case of lasso regression, it will set the parameter values 0. It can do that. Okay, it can do that so that it can exclude some of our feature values. Those are not important. Okay, so this is a special selection. That means lasso regression, it will do the shrinkage, and two things we can get better. The shrinkage, that means the overfitting problem, it can remove, and it can also select the best features from our data set. Another feature it will just consider 0. Okay, so this is a special quality of lasso regression. So here is the differentiation towards it. Can do that. So one proof is there. That is why ridge regression cannot make the 0. Okay, cannot make the 0. That is the beta value cannot make the 0. Why? We can see that if we do already do these things already. Okay, that means this is our equation, and then this equation we can, if we consider just only one beta, then if we will get this. For simplification, we will consider just one beta. Okay, and then y minus of x base. So it is like if we just you can see from this part, y square minus of x beta square. So y square 2ab, then b square something. Okay, y square minus 2 y xb plus of x square and beta square, and here's the lambda beta square, it is equal 0. Then if we do the derivative of this equation, okay, do the derivative of this partial derivative, then we will get this. And from here we can see that we can find out the beta. The beta will be 2xy divided by 2 x square plus lambda. This one, okay, this one is the equation. And we can see that actually the beta will never be 0. Why? Because to make it, to make this equation 0, what we have to do? We have to consider this lambda equal infinite. Okay, so this lambda equal infinite. So usually we will not consider that one, and so we will never get the beta equal 0 in ridge regression. Okay. And if we get the 0 also in denominator, we can see that it will be undetermined on that case. So that means the beta will never be 0 for our ridge regression. So here is the, instead of beta square, we have just beta. Okay. So if we consider the same, that means I can just want one beta, and we do the same. So that means the partial derivative, we will get this, and then finally beta will be this one. Okay, so we can see that now the beta can be 0. Why? Because this part minus of the lambda. Okay, minus of the lambda. So the numerator part can be 0. Okay, why? Because the 2xy, if lambda is the same, okay, here the difference. So the difference can make the 0. Okay, so that means in this equation we can see beta can be 0. So in lasso regression we will get that beta value 0. That means it will do the feature selection. the Ridge and lasso regression, combining the effort of Ridge and lasso, usually the elastic net, another regression mechanism. Elastic net is actually constructed. Okay, so in this case, it will use the penalty term from lasso and Ridge. So this part is from the Ridge regression, and this part is from lasso regression, and it will actually provide us the more benefit. Okay, more benefit. So in this case, we can see that means this is called the elastic net, another regression method. And one thing you can see that is, those are just proposal. Okay, at first the Ridge regression is proposed, and then some other researchers proposed just lasso regression, and some other researchers they combine the effort of Ridge and lasso and propose the elastic net. Okay, so this is how usually we do the research. Okay. Um, so in this case, what's the benefit of combining this? The combining benefit is it just combines the benefit of Ridge and lasso regression. So the lasso, it has some limitations. The limitation is that for large P and a small n, what does it mean? It means that large P means our parameters, or we can say features. If we have large number of features and a small number of cases, or we can say instances, usually we call it the high dimensional data with few examples, that means few instances. We have just few data, but the dimension of data is very high. On that case, lasso selects at most n variables and remove the others. Okay, so it will affect the performance. So there is the group of highly correlated variables. Then lasso tends to select one variable from a group of and ignore the others. Okay, so this is a limitation. To overcome this limitation, the elastic net adds the quadratic part. That means on that case, the Ridge regression will take part. Okay, so that it will not consider those variables. So elastic. Now I think it's better to go for just only uh, the example. Okay? Example, we have already discussed lots of theories for lasso, Ridge, and elastic net. But if in the exam some kind of like data set is given, then how can we solve those? So like here the data set is given, this is the data set. And we can see that in this data set, it is like the athletes, there is number of athletes and participated events and number of medals for different teams of maybe you can say of the world. So like Switzerland, the
So,
number of
Norway,
athletes
Sweden, Jamaica.
participated in Olympic it is like 151
স্যার
and then
আপনার
number of
কথা
events
স্যার
about
ভেঙে ভেঙে
10
আসছে।
events.
কথা কেটে কেটে আসছে।
So similarly for the Norway, Sweden, to predict the meditative.
স্যার কথা শোনা যাচ্ছে না স্যার, কেটে কেটে আসতেছে।
হ্যাঁ দেখতেছি আমি ইস্যুটা। হ্যাঁ let me see, check that. হ্যালো, হ্যাঁ এখন শোনা যায়?
জি স্যার, এখন শোনা যাচ্ছে।
Okay. So if we want to apply the linear regression, and in this case, the equation is this. Okay, equation is this. So we can just make this equation, this data set, like this is our y. So this is our y, and this is our x. Okay, this is our x. So here is, we can see in x we have these just two columns, that is two features, and we have this y. And b, in our b, that is, we have the slopes. Okay, the slopes, beta 1, beta 2, and we have also, we need to consider also the beta 0. Okay, as we have to consider the beta 0 without any coefficient, you can say that there is no variables here with beta 0. So for the beta 0, we need to do the augmentation. That is, we have added just 1, 1, 1, and 1 for all these cases. Okay, this is our augmented x. So this, just by adding extra we can say the extra column. Okay, extra column 1, 1, 1, 1, because this extra column will be for this one, that is the beta 0. Okay, because there is no x in beta 0. There is no x in beta 0. Okay, so in beta 0 it is just beta 0 constant. But beta 1, it has x. And also we can see that, like, if we have this the beta 2, then here's the beta 2. Okay, now so this is the case. Okay, this is the case. Actually we have to solve this one. So what does it mean? It means that y equal xb. Okay, xb. Now if we just multiply the both of the side using x transpose, so here is the x transpose and here is the x transpose b. And now we can see that there is the x transpose. So that means x transpose y. So x transpose y equal x transpose xb. So x transpose xb. X transpose x, that is inverse. There is also x transpose x inverse. Both of the side you can multiply with the same thing. And now we can see that actually what we can get. So from this part, we can see that this part is x transpose x, and this part is x transpose x inverse. So we can, what we can do, we can cancel these two out. Okay, because x transpose x inverse and x transpose x, so we can cancel these two out, and then we will get b only. So here is the b, and here is the x transpose x bar. So x transpose x, then the inverse x transpose y. So we will get this one for our linear regression. And that's what I have already mentioned here in our equation also. Here is this. That means for our linear regression, this is the equation for that. Okay, and for our ridge regression, this is the equation where we have to consider lambda and IP. Okay, okay. So in this case, if we apply this equation to our, we can see this is x. We have the x and x. This is the x. Okay, this is the x, and we have the x transpose. So here is the x transpose. So x transpose x, we have to multiply these two. Then we will get what? We will get this. That is x transpose x. And then if we do that is the inversion. Okay, if we do the inversion, that means inverse of this matrix, then we will get this. Inverse of this matrix, we will get this. So x transpose x inverse, we will get this matrix. Okay, so that means in this case we can see that to solve this equation, what we have to do, x transpose x inverse, then we have to again calculate the x transpose of y. We can calculate easily, and then multiply these two, then we will get the b. What's the b? B is the parameters. Okay? B is our parameters, b0, b1, and b2. So we will get that there is intercept and slope value. Okay. So few things we have to remember here. That is, this is just only for ordinary least square method, but we didn't use the lasso or ridge regression in this case. In case of linear regression, whatever we have already seen, there is x transpose x. Sometimes we will get the x transpose x like this. Why? Like maybe if our data set have the features like the similar features, that means feature 1 and feature 2 the same, or we can say in this case like the feature 2, the values of feature 2, it is like the there is 2 times of feature 1, 2 times of feature 1. So 2 times of feature 1 will get the feature 2. So if we have this kind of, maybe we will not get this one frequently, but sometimes we will get, because when we consider lots of features, there might be some relationship like this. Okay, so usually we call this on a collinearity. Okay, so if we have those collinear the features, then find out the x transpose x, then this matrix will not be inverted. We cannot invert this one. That means we cannot get the inverse matrix of this one because of the singularity of this matrix. So usually we call it singular matrix. Okay, singular matrix. So that means in this case we can also see that this third column, the column 3, we can find out this 2 times of column 2. So this matrix is singular matrix. We cannot, that is, find out the inverse matrix of a singular matrix. So this is a problem. Okay, in case of linear regression. But in case of Ridge regression, if we apply the Ridge regression, that means x transpose x plus lambda I. Okay, so here is the lambda. If we consider lambda equal 5, anything we can consider, and I is this. This is not actually the I. It is called the pseudo I, because we can see here is 0. Okay, and others. Why it is 0? Because the lambda beta 0 is there. Okay, so we don't want to penalize this beta 0. We just put, okay, if we do that, then now it is changed. Okay, it is changed because you can say this is added. Okay, this is added. So this addition make this matrix invertible. Okay, we can invert this one. We can find out the inverse matrix of this matrix. So that means that the Ridge regression solves one of the big problem. That means in data sets, sometimes we can see if we apply, there is a least square method for finding out the solution of linear regression, we cannot find. But if we apply the Ridge regression, it will find that. Actually, the term Ridge is from here because we can say it and then we have to find out the inverse of this. Hello, hello.
জি স্যার, শোনা যাচ্ছে।
Yes, sir.
Am I audible?
Yes, sir.
Yes, sir.
এই ডিসকাশনটা কি শুনছো?
No, sir.
না স্যার, এতক্ষণ শোনা যাচ্ছিল না।
না স্যার, শোনা যাচ্ছিল না।
Okay, তাহলে আমরা that means if we have a given data set, then how can we solve the ridge regression problem? So here is the ridge regression solution for the ridge regression problem. The step one, that is first step, is to standardize the feature values of the data set. So that means if the data set is given, so this is the original data set we have, this is original data set. What we have to do, we have to find the standardized value. Though what does standardized values means? It means subtract the mean feature values from every feature. At first we have to find out the mean of maybe this athletes mean value of this, like this, the mean, it is like x bar. So we have to subtract the mean from each and every value, like 151 minus of x bar, 69 minus of x bar, 198 minus of x bar, and 75 minus of x bar. And we have to find out the standard deviation of this data. So that means if we can say that this is sigma, so what we have to do, we have to calculate this one, x minus of x bar, and divided by the sigma. Okay, then we will get this value, that 0.4, then minus of 0.9, 1.2, and 0.8. Then next, what we have to do, we have to think another feature like events. This is another feature. So similarly, we have to standardize this. That is at first we need to find out the mean value and then divide this one by the sigma. Okay, sigma of
So, sir, for each feature, we will,
the
sir,
event.
for each feature, we will find the
That means,
mean and then minus from all the
standard deviation of
attributes.
events. Then we will get these values. Okay. So now our x will
share of a
x here is the athletes 0.9 has a 0.4 minus 0.92 minus 0.5
স্ক্রিনটা
and
দেখা
events
যাচ্ছে না।
is we have to do the augmentation
স্ক্রিনটা
by.
দেখা যাচ্ছে না।
So that means we have already prepared our x.